Hello everyone, this is Jesse Crawford with Tarleton State University, and this is going to be our last video in Chapter 4 of the Foundations of Mathematics course, covering cardinality of infinite sets. We actually started section 24 in our last video and covered a lot of really important information about functions, and that lays the groundwork for this section, which is an incredibly interesting topic. I don't think it's an overstatement to say that the material in this section is truly astonishing. There are some really surprising results in this section, and in a lot of ways, these ideas kind of unlock the gateway to more advanced topics in mathematics that you'll see in courses like real analysis and abstract algebra. So, what are we talking about in today's video? We're looking at cardinality of infinite sets. Now, we're all familiar with the idea that a finite set has a cardinality. So, for example, a set that contains 5 elements has a cardinality of 5. What we're going to do today is extend that notion to infinite sets, and we'll be able to talk about the idea that two infinite sets can actually have different sizes. So, there are different sizes of infinity, and for that matter, there are actually infinitely many different sizes of infinity. This gets us into some territory that's incredibly interesting, aesthetically very beautiful, and really demonstrates how large the world of set theory and mathematics can really be. With all that said, let's go ahead and jump into the material. So, the first thing I wanted to do in this section is just review what a one-to-one function is. We saw this definition in our last video. And we actually use this definition on some examples. For example, we proved that the function from r to r defined by f of x equals x cubed is 1 to 1. And this definition is perfectly suited for this. This definition says that if you take any elements of your domain, that if f of the first element is equal to f of the second element, then those two elements are actually equal to each other. And this is great for doing proofs. Like this is the proof that we showed last time for showing that f of x equals x cubed is 1 to 1. And because of the structure of this if-then statement, you simply assume, you start off this proof by assuming that f of a1 is equal to f of a2. And if you're able to deduce that a1 is equal to a2, you've shown the function is 1 to 1. And this is all fine. The problem that I have with this definition is I don't think it actually intuitively captures what 1 to 1 is. And if we want to capture that in a more intuitive way, we can simply take the contrapositive of this, and we all know how to do that. We'll change the order of this if-then statement and then negate each part, and we get this. So the contrapositive of this would say that for any two elements of your domain, if those two elements are not equal, then the output values corresponding to them are not equal. And suddenly this contrapositive, it does a really good job of explaining intuitively what 1 to 1 means. What 1 to 1 means is if you take two different input values, those will always correspond to two different output values. And this shows up in a picture like this. So this is a great example of a function that's not 1 to 1, right? Because we have two different input values here that are mapping to the same output value, and that means this function is not 1 to 1. Now, we looked at this result last time. This says that if a and b are finite sets and f is a function from a to b, if the cardinality of our domain is bigger than the cardinality of our codomain, the function that we're dealing with cannot be 1 to 1. And this picture really illustrates why, right? Because if your domain's bigger than your codomain, you're going to have to double up. Some of these input values are going to get sent to the same output value. But as we just saw in the previous slide, that means the function is not 1 to 1. Now, speaking of contrapositives, I'm going to delete this picture, and I want to look at this if-then statement and look at its contrapositive. So let's reverse the order of the if-then statement. Instead of this saying f is not 1 to 1, this is going to say f is 1 to 1 because we're negating it. And instead of this saying the cardinality of a is greater than b, it's going to say the cardinality of a is not greater than b, which means the cardinality of a is less than or equal to b. So this statement here and this statement down here are completely logically equivalent to each other. So yeah, this says that if f is 1 to 1, the cardinality of the domain has to be less than or equal to the cardinality of the codomain. And we can see a picture of this. These are kind of the two examples that can occur. This is an example where we have a 1 to 1 function, and our domain has a smaller cardinality than our codomain. This has 3 elements and this has 4 elements. And then this is an example of a 1 to 1 function where the domain and codomain have the same cardinality. So both of these are possible. The domain could be strictly smaller than the codomain, or they could have the same size. And as a quick reminder, when you have a bijection between two sets like this, the cardinality of the domain and the codomain must have the same size. Now, this entire slide is only, right now, we're only considering this for finite sets. But this slide is actually going to form our definition for the cardinality of an infinite set. So let's get started with that. So here's our definition. This says let A and B be sets. Notice it doesn't say finite sets. They could be finite or infinite. If there's a one-to-one function from A to B, we just saw in the previous slide that would imply that the cardinality of the domain is less than or equal to the cardinality of the codomain. And that's actually what our definition is going to say. If there's a one-to-one function from A to B, then we say the cardinality of A is less than or equal to the cardinality of B. And we have a symbolic way of expressing that here. So it's sort of like this curvy less than or equal to sign. And so this says the cardinality of A is less than or equal to the cardinality of B. That's how we read this here. Now, what we also saw in the previous slide is that we have a bijection. If there's a bijection from A to B, in that case, we say the cardinality of A is equal to the cardinality of B. And the way that we will write that is with this kind of curvy equal sign. And that's how we will express that idea. So both of these ideas will be useful for us today. Let's look at some examples of this. So in this example, we have a set A, 1, 2, 3, and a set B, which has 4 elements from a few different numbers here, between 48 and 99. And let's show by this definition that A has a cardinality less than or equal to B. So we have a function f. Now, this actually is a function f. This looks kind of weird to say that this is a function, but as a reminder from last time, a function is a set of ordered pairs. So it's a relation that has the property that every domain element is related to a unique codomain element. And it might almost be helpful to express this in tabular form. So you can see we have an input value, which is either 1, 2, or 3, and these are the corresponding output values. And we can see this is a function because every domain element is associated with a unique codomain element. And in fact, this is a one-to-one function because for any two different inputs, the outputs are also different. So this is a function from A into B, and it is one-to-one. And what this proves is the cardinality of A is less than or equal to the cardinality of B. And again, this is the notation that we're going to use for that. Now, this is kind of a silly example because we already knew this. Like, we know the cardinality of A is 3, and we know the cardinality of B is 4. But again, what this slide is doing is it's extending that definition of cardinality to sets that are potentially infinite. So we do want to make sure that this definition still agrees with the notion of cardinality that we already had for finite sets. And this example suggests that that is the case. All right, let's look at this example where A and B are both equal to the set 1, 2, 3. We can simply define a function f from A to B with the definition f of A is equal to A. This is called the identity function because the output corresponding to any input is simply equal to that input. And it's really easy to see that this function is one-to-one. Keep in mind that a function is one-to-one if two different inputs are going to correspond to two different outputs. And of course, if you plug two different input values into this function doesn't even change those inputs. And so they're still going to be different when they produce those output values. So this is a one-to-one function. And according to this definition, if we have a one-to-one function from A to B, then the cardinality of A is less than or equal to the cardinality of B. Or we might even just say the cardinality of A is less than or equal to the cardinality of A because A and B are equal to each other in this situation. Now, again, this is kind of a trivial result because we already knew that the cardinality of A is less than or equal to the cardinality of B because they both have cardinalities of 3. But this is a good example to look at because we really do want to keep in mind that this really is a less than or equal to sign. It doesn't mean that the cardinality of A is strictly less than B. It means less than or equal to. And so it does include the possibility that these two sets have the same cardinality. All right, let's look at this example now where we're looking at the set of integers and the set of real numbers. Intuitively, it seems that the cardinality of the integers should be less than or equal to the cardinality of the reals because the integers are contained inside of the reals. And we can actually just use the same strategy we used on the previous slide. We can just define a function f from z to r by f of a is equal to a, Because every integer is contained in the reals, this actually does define a function from the integers into the reals, and it's one-to-one for the same reasons that we discussed on the previous slide. And so this does prove, in fact, that the cardinality of the integers is less than or equal to the cardinality of the reals. So at this point, we're starting to realize that this relation serves some of the same functions that the less than or equal to operation serves in the real number system. We know that the less than or equal to relation in the real number system serves as an ordering. And we actually talked about partial orderings back in chapter 3 when we were discussing relations. And partial orderings have the property that they are reflexive, transitive, and antisymmetric. Now, this relation is actually not antisymmetric, but we can show that it's reflexive and transitive. And in a moment, we will actually show that it has a property that's kind of similar to the anti-symmetry property that the less than or equal to relation has in the real number system. But yeah, let's just talk about reflexive and transitive real quick. So let's show quickly that this is reflexive. In order to show that, we would need to show that for any set A, the cardinality of A is less than or equal to the cardinality of A. Of course, that's intuitively clear, but we do want to make sure this definition is actually upholding that intuitive idea. In order to do that, we just need to let A be an arbitrary set, and we need to produce a one-to-one function from A to A. And of course, the one that works is the one that we discussed earlier. We simply let f be the identity function, f of A equals A. And this little bit of logic shows that this really is a one-to-one function. This is quite straightforward. This is the definition of a function being one-to-one. It would say that if f of a1 is equal to f of a2, then a1 has to be equal to a2. But of course, this is true because f of a is a. So this statement here follows directly from this just by definition of f. So this is indeed true, and this means that this function is one-to-one, and that proves that because there's a one-to-one function from a to a, the cardinality of a is always less than or equal to the cardinality of a for any set. So this is a reflexive relation. And that's good news because intuitively we would like this to be true. Okay, let's look at transitivity now. So for transitivity, we would like for any sets A, B, and C, if the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of C, we would like the cardinality of A to be less than or equal to the cardinality of C. So this is kind of saying if A is a set that has a smaller size than B, and B has a smaller size than C, then intuitively we would want A to have a smaller size than C. And this is actually true, and we're going to show this right now. Okay, so let's assume that A, B, and C are sets where these statements hold. Now, by definition, if this is true, then there exists a function f from A to B that is one-to-one. That is the definition of this statement. The definition of this statement is that there is a one-to-one function from B to C. Now, if we have these functions from A to B and from B to C that are one-to-one, one thing we can do here is create a composition function g compose f, and this is going to map A all the way into C. And we've seen how to do composition functions in like college algebra classes. Basically, g compose f of A is just g of f of A. Now, it turns out that g compose f must be one-to-one. If f is one-to-one and g is one-to-one, g compose f is one-to-one, and we can just show that right now. In order to show that, we simply need to show that for any two elements of our domain A, if g compose f of a1 is equal to g compose f of a2, it follows that a1 is equal to a2. So let's just assume that we have two elements of our domain and that this statement holds. Well, if this statement holds, then by definition, what is g compose f? It's g of f, right? So by definition, that would mean that g of f of a1 is equal to g of f of a2. Now let's ask ourselves, is it possible that this element f of a1 and this element f of a2 are different? Could that be true? And it actually can't be true. We know it can't be true because this function g is one-to-one. And if a function is one-to-one, that means if the output values are the same, the input values are the same. In fact, that's just the definition of one-to-one. So because g of f of a1 is equal to g of f of a2, it follows that f of a1 must be equal to f of a2 because g is a one-to-one function. But now we can realize that f is a one-to-one function. So if f of a1 is equal to f of a2, it must follow that a1 is equal to a2. And so at this point, we've gone all the way from this assumption to this statement. But that means that this implication up here holds, and this is simply the definition that G compose F is 1-to-1. So G compose F really is 1-to-1. That's what this argument demonstrates. And because there is a 1-to-1 function G compose F from A to C, by definition, the cardinality of A is less than or equal to the cardinality of C. So anyway, these two results, they're pretty straightforward. I mean, and again, they're intuitively almost just obvious. Like if we have a small set that has a size less than or equal to a medium set, and a medium set is less than or equal to a large set, then the small set should have a cardinality less than or equal to the large set. This is just intuitively super clear. And then this result is just saying that for any set, the cardinality of that set is less than or equal to its own cardinality, which is completely intuitively clear. But I did just want to go through these arguments to show you this is formally how you demonstrate that these definitions really do satisfy these properties. So with that in mind, we said here that this relation is reflexive and transitive, and it's not antisymmetric, but there's something kind of like an antisymmetric property that we can have, and that's what this slide is going to tell us about. Now, this is the Cantor-Schroeder-Bernstein theorem. This is a very deep theorem that is quite difficult to prove, and we're not going to get into the proof of this today, but I would encourage you to look into this. This says that if A and B are sets, and if there exists a 1-to-1 function f from A to B, and a 1-to-1 function g from B to A, then it turns out there must be a bijection h from A to B. Now, what does this really tell us for our purposes today? If there's a 1-to-1 function f from A to B, that means by definition that the cardinality of A is less than or equal to the cardinality of B. And if there's a 1-to-1 function g from B to A, that means the cardinality of B is less than or equal to the cardinality of A. And if there's a bijection from A to B, that means that A and B have the same cardinality. So what is this really saying? It's saying that if the cardinality of A is less than or equal to the cardinality of B, and if the cardinality of B is also less than or equal to the cardinality of A, then intuitively they should have the same cardinality, and that is indeed true. Now, that doesn't mean that the set A is equal to the set B. It just means they have the same cardinality. So, for example, A might be the set 1, 2, 3, and B might be the set 11, 12, 13. In both cases, they have the same cardinality, but they're not actually equal to each other. And so we get a property that kind of looks like antisymmetry, but technically it's not antisymmetry. What about, so we've gone through a lot of the properties that this relation has, but what about this relation? Can we say something about the relation that says that two things have the same cardinality? What kind of properties does this have? It kind of looks like it should be an equivalence relation. And an equivalence relation is reflexive, symmetric, and transitive, and in fact, that is the case for this one. I'm not going to go through these proofs in detail because we just went through some other ones in detail. And these proofs are really straightforward. I'm going to give a quick outline for each one of these. How would we show reflexivity? We simply need to show that for any set A has the same cardinality as itself. All that means is you have to get a bijection from A to A. And again, the bijection that works is the identity function f of A is equal to A. It is completely straightforward to show that this is bijection. So I'll just sort of omit that from the discussion here. What about symmetry? We would need to show that for any sets A and B, if A has the same cardinality as B, then B must have the same cardinality as A. And again, what would that really require? It would mean that if we have a function from A to B that is bijective, we need to produce a function from B to A that is bijective. And a really nice property that we saw last time about bijections is every bijection has an inverse function that goes in the other direction. And again, it is quite straightforward to show that if f is a bijection, then its inverse function is also a bijection. Last thing to show is transitivity, and we basically just went through this argument. If A has the same cardinality as B and B has the same cardinality as C, then there are bijections. There's a bijection from A to B and a bijection from B to C, and we can simply look at the composition function. We basically already proved a couple slides ago that if this is 1-to-1 and this is 1-to-1, that this is 1-to-1. And it's also very easy to check that if this is onto and this is onto, then this is onto. So this completes that argument as well. So again, every single one of these properties, it's totally intuitive. A set has the same cardinality as itself. The notion of two things having the same cardinality is symmetric, like, the order doesn't matter. And this sort of transitive idea holds. these two sets have the same size, and these two sets have the same size, then these two sets have the same size. So these are all very natural results, but we can also formally demonstrate that they're true. So now that we have demonstrated that we can create a concept of cardinality for infinite sets, we are now prepared to explore one of the most fundamental concepts in advanced mathematics, which is the idea of countable infinity versus uncountable infinity. And that's what this definition is going to do. So this definition says let A be a set if the cardinality of the natural numbers is the same as the cardinality of A, then we say that A is countably infinite. And what I'm doing here is I'm essentially repeating that definition, because if the cardinality of the naturals and the cardinality of A are the same, well, that means there's a bijection between them. In fact, this is how a lot of books will define countably infinite. They'll skip over this and they'll just say, if there's a bijection from the naturals to a set, that set is called countably infinite. Now, if a set is finite or countably infinite, we are going to say that it's countable. So there are certain situations where it's useful to sort of put finite sets and countably infinite sets in the same category, and that category is going to be called countable. But then there are also sets that are neither finite nor countably infinite. Those sets are called uncountably infinite. So just to get a sense of what these definitions are telling us, let's look at some examples. So here's a quick one. This set 1, 2, 3 is finite. And again, we will consider finite sets countable. So any finite set is considered countable. This is a countable set. What about this set? If we're looking at the set of natural numbers, does it have the same cardinality as the set of natural numbers? And the answer is yes. We saw earlier that this relation is reflexive. Every set has the same cardinality as itself. So the set of natural numbers has the same cardinality as the set of natural numbers, but that means it is countably infinite. Another way to say that is there is a bijection from the set of natural numbers to itself. It would be the identity function. Now, what might be more surprising is that the set of integers is also countably infinite. Again, we just need to check that there's a bijection from the naturals to the integers, and so this is countable. What's maybe even more surprising than that is that the set of rational numbers is also countably infinite. And we're going to show these results on the next couple slides. We'll actually prove these statements. The first example of a set that we can encounter that is not countably infinite is the real numbers. The real numbers is obviously not a finite set, and we'll show pretty soon that this is also not countably infinite. Therefore, this is our first example of an uncountably infinite set. So let's go ahead and demonstrate this fact and this fact, and we'll do that on the next two slides. Okay, so here's our proposition. We want to say that the integers is countably infinite. Now again, that's going to be true if there's a bijection from the naturals to the set that we're considering, which again is the integers here. So what would that look like? Well, this is the set of natural numbers, and this is the set of integers, and we want to show a bijection between them. Well, we've seen before that a bijection is a one-to-one correspondence. So here I'm writing out a one-to-one correspondence. And we have this nice property for the naturals. This is why the naturals is really so useful in this definition. The natural starts at 0, and then it just proceeds in order. So if you're trying to create a one-to-one correspondence between the naturals and some other set, you just start at 0, and you just come down like this, 0, 1, 2, 3, and so on. And then you simply need to list out the elements of the other set in this column. Now, there's a bit of a challenge working with the integers here, because the integers don't just go out in the positive direction, they also go in the negative direction. So how can we list them out in this way? And this example shows how that works. You would simply list 0 first, and then you would just alternate. You just go 1, -1, 2, -2, 3, -3, and just continue in that way. What can we actually say about the function that we've defined here about this one-to-one correspondence? First of all, it is true that this is a one-to-one mapping. You'll notice that every integer that appears in this list, it never appears more than once. Every integer appears in this list exactly once. So it's impossible to find two different input values in this setup that correspond to the same output value. So this actually is a one-to-one function. And it's also an onto function because every single integer does appear in this list eventually. So this mapping is one-to-one and onto, and therefore it is a bijection. Now, we're kind of going to a lot of trouble to illustrate what this bijection is. Probably a more efficient way to think about this is that we can simply list the elements of the integers And of course, if we can list a set of elements where every element appears eventually in the list and they never repeat, then that automatically defines a one-to-one correspondence because the naturals can be listed as well. So this is a more efficient way to show that a set is countable. You just create a list that has all the elements in it with no repeats. All right, well, let's go to our next result. We want to show that the set of rationals is also countably infinite. Now, as a reminder, rational numbers are simply fractions where the numerator and denominator are both integers, and of course our denominator can't be 0 here. And we're going to show that this is a countably infinite set. How do we do that? Well, we just need to list them. We need to create a list that has all the rational numbers in it. And this requires quite a bit more work. Let's set up the following array. This array has every single positive rational number in it. How can we see that? You'll notice that this first row has every single rational number in it where the numerator is 1, right? So we have 1 over 1, 1 over 2, 1 over 3, 1 over 4, and that just continues in this way. The second row has every positive rational where the numerator is 2. And then this one has every one where the numerator is 3. So what that means is every single positive rational is going to be in this array somewhere. But the question is, can we actually list all of the elements in this array? How can we do that? Well, these red arrows actually show us how we can do this by sort of zigzagging around. So you just kind of traverse this array in the following manner, and this gives you a definite order to go in, and you will eventually get to every single element in the array. So the list would look like this. So we would start 1 over 1 is 1. 1 over 2 is 1 half. 2 over 1 is 2. 3 over 1 is 3. Now you'll notice that we skip this element. So this is 2 over 2. But 2 over 2 is 1, and we've already got 1 in our list, so we just skip over it. Because again, we don't want this list to have any repeats. We just want it to list every single element in the set exactly once. So you just continue in this way and list all of the elements in the following manner. Now, there is a problem with this list where this is only a list of the positive rational numbers, but rational numbers can be negative, right? If you just take like a negative number divided by a positive number, you will get a negative number. And there's also the issue that 0 is a rational number. So like 0 divided by anything is 0, and 0 is not in this list either. But we can easily fix that using the method we discussed on the previous slide. We can simply put 0 first, and then we can list these elements and their negatives by alternating. So we can do 1 negative 1, 1 half negative 1 half, 2 negative 2, and so on and so forth. And now every single rational number is in this list exactly once. And so we can then use this to define a bijective correspondence between the naturals and the rationals, and that proves that the rationals are a countably infinite set. All right, so our last result here, we're going to prove that the real numbers is uncountably infinite. Now, proving this directly might be a bit much for us to handle, so we're going to do something a little bit easier first. We're going to prove that the closed interval bracket 0, 1 is uncountably infinite, and because this is contained inside of the reals, that will immediately prove that the reals is also uncountably infinite. Well, we might want to remind ourselves a little bit about, what the numbers in this set look like. This is all of the real numbers between 0 and 1, and this is going to contain a bunch of fractions. It's easy to see that there are infinitely many things in this interval because every fraction of the form, like 1 over 2 is in here, 1 over 3 is in here, 1 over 4 is in here. All of those fractions are in here, so there are infinitely many things in here. And every element of this set has a decimal expansion. So for example, 1/3, we just have 0.3 repeating. And a number like 1 is in here. This would be 1.0 repeating. Now, there's kind of an unfortunate, kind of inconvenient property of the decimal number system, which is there are certain numbers that can be expressed in two different ways. So on the one hand, the number 1 is equal to 1.000, where this just repeats forever. But on the other hand, the number 1 is actually equal to 0.9999 repeating. I am not saying that this is approximately equal to 1 or anything like that. No, it literally is 1. And we can prove this. Rigorously, we can prove this. Maybe a really easy way to see it is, if you think about it, if 1/3 is 0.33 repeating, well, if you triple both sides of this, the right-hand side is 0.9 repeating, and 1/3 times 3 is 1. So this really is true. You can prove this using some results from infinite series and calculus 2 to show that this is the case. So yeah, there's actually two different ways to express the number 1, and this extends to another situation. Like if you have a number like 1/4, you can write this as 0.25, and then of course from that point onward, there's just zeros after that. Well, in the same way that this repeated 0 can be replaced by repeated 9s by decrementing this value, these repeating zeros can be replaced by repeating 9s here by decrementing this 5 down to a 4. So yeah, there's certain numbers in this interval that have two different ways to be expressed. Now there are other numbers that don't, like the number 1/3. There's only one way to express that, and that's 0.3 repeating. And then of course there's an additional complication that we need to keep in mind, that there are irrational numbers in this interval too, right? So this contains all the rational numbers between 0 and 1, but it also contains all the irrational numbers like this number. So in the next slide, we're going to prove that this interval is uncountably infinite, but I want to set a convention up. The convention is that if I have a number that can be expressed in two different ways, I'm going to choose the one that has infinitely many 9s. I do not want to choose the one that has infinitely many zeros. One reason for that is just because I actually want all of my numbers to start with 0, and the number 1 actually starts with a 1 here. So by making that choice, everything will be 0 point something. Once you've made that setup, once you've decided to make that assumption, then any two real numbers will be different if they're different in a single position. So like the number 1/3 is obviously different from the number 1/4. What do you need to do to demonstrate that? If there's even a single point where they're different, like there's a 3 here and there's a 2 here, that means they're different. And that only works because we're making this assumption, because again, there's a 0 here and there's a 9 here, but these two are the same number. But once we choose to only look at expansions with infinitely many 9s and not have any expansions with infinitely many zeros, this is no longer a problem. Now, I do want to say one more quick thing just to cover my bases. There is one number in this set that will have infinitely many zeros, and that's the number 0 itself. But there's no way to re-express that with infinitely many 9s, so we don't have to worry about that case. All right, well, anyway, with all those caveats out of the way, let's go ahead and prove that this interval bracket 0, 1 is uncountably infinite. So we'll go ahead and do that now. The proof technique that we're going to use is proof by contradiction. So we will assume that bracket 0, 1 is not uncountably infinite and show that that results in a contradiction. Now, we've already said that this interval is infinite, right? There's infinitely many fractions in here. So if you're not uncountably infinite, you must be countable, but it's also not finite, so it must be countably infinite. Well, if this interval is countably infinite, that means there exists a bijection from the natural numbers to this interval, and that takes the form of a one-to-one correspondence. So the natural number 0 maps to some number in this interval, and every number in this interval can be expressed as a decimal expansion. The number 1 maps to some number in this interval. The number 2 maps to some number in this interval, and that just continues on and on. Now, we're basically setting up a notational device where, like, this is the number 0, and so the first subscript in every single one of these decimal entries is a 0, and then you can see they're listed out. This is 0, 1, 2, 3, and so on. And then from that point, like if this is a 1, the first subscript here is going to be a 1, and it's also A10, A11, A12, A13, and then this is a 2, so this is A20, A21, A22, A23, and so on. So every single digit that appears in this entire array has a unique subscript identifier that we've set up here. All right, so with this setup in mind, we will now produce a new number x. Now this is just one number, so I don't have to have two subscripts on every one of its decimals. I just need one, and I will start at 0 again, just like we did up here. So this number x is 0.b0, b1, b2, and so on. This is the decimal expansion. And what we are going to do is deliberately set this number up in such a way that it is not equal to any of these decimals. It will not be equal to this number. It will not be equal to this number. It will not be equal to this number. We're going to use a technique called Cantor's diagonalization argument. The reason it's called a diagonalization argument is because it looks at the diagonal. So for example, we're going to look at this digit A00, and we're going to set this up in such a way that this digit B0 will not be equal to this digit A00. Then we're going to look at A11, and we're going to set this up in such a way that A11 will not be equal to B1. And then we'll say that A22 will not be equal to B2, and we're just going to continue all the way down the diagonal. How do we actually accomplish this? Well, we just need to set it up in such a way that these b values are not equal to these diagonal entries. Now, what do these diagonal entries look like? They're of the form a sub nn. So one really simple idea is just whatever a sub nn is, just add 1 to it, right? So you just take a sub nn and add 1 to it. But we have a bit of a problem if a sub nn is equal to 9. This doesn't make sense because 9 plus 1 is 10, and 10 is not a digit. We're only considering digits between 0 and 9 right now that can be in a decimal expansion. But that's fine, because what we can do is we'll just say that if a sub nn is not 9, we'll add 1 to it. And if a sub nn is 9, we'll just give it some arbitrary value. Let's just say 7. You could do 5, you could do 2, whatever you want here. You can't do 0 because we don't want to get into a situation where we have repeated zeros, as discussed on the previous slide. Now, what is the consequence of this definition? If a sub nn is not equal to 9, then b sub n is going to be that number plus 1. Well, if I take a number and add 1 to it, I get a different number. If a sub nn is equal to 9, then this bn value is equal to 7. And again, that's a different number. So the result of this definition is that bn is never equal to a sub nn. So again, what that's saying is this number here is not equal to this number here. This number here is not equal to this number here. And this number here is not equal to this, and so on and so forth. Now, what is the point of this? What does this really accomplish? Well, now you might ask yourself the question, could this entire decimal number x be equal to this entire decimal number here? And the answer is it can't be, because this first digit is not equal to this first digit. So x is not equal to this first number. Is it possible that x is equal to the second number? And it can't be, because this diagonal entry here does not equal this. And that just continues in this way. So what we've effectively done here is we've produced a decimal number x that is not anywhere in this list. And in other words, we can say the following. For every n in the natural numbers, f of n is not equal to x. But on the other hand, x is a decimal number, and you can see here that it's starting with 0, and it is a positive number. And therefore, x is in this interval, bracket 0, 1. And what this says is that x is not equal to any of these f values here, and that means x is not a possible output value of the function f, so this function f is not onto. If the function f if this function f were an onto function, then that means every single element of this interval has to be an output value at some point in this process. But we've just created a number x that is not an output value ever, and that means this function's not onto. But if it's not onto, it's not a bijection. And we actually assumed up here that it is a bijection. And so this is a contradiction. And so where did this contradiction come from? It ultimately came from this initial assumption that bracket 0, 1 is not an uncountably infinite set that ultimately led to this contradiction. And we're familiar with our proof by contradiction technique. That means this initial assumption is not true. I thought it might be helpful to look at an actual example, because this is a little bit convoluted how we set this up. So this example basically just says, what if these are the specific numbers that were given in this diagonal array? How would this actually work? And so again, you can see it focuses on the diagonal, and the algorithm that we set up earlier is anytime we don't have a 9, we just add 1. So like this 4, we add 1 to it, we get 5. This 2, we add 1 to it, we get 3. And anytime we do have a 9, we just change it to an arbitrary value like 7. So this 9 here, we put a 7. And what you'll notice is that you get a number like this number 0.573, and just ask yourself, is this number equal to this number? No, because 5 is not equal to 4. Is this number equal to this number? No, because 7 is not equal to 9. Is this number equal to this number? No, because 3 is not equal to 2. So what we've done is we've taken what appears to be a one-to-one correspondence, and we've shown that there must always be a decimal number we can create that is not in this one-to-one correspondence. But that actually just means you can never produce a one-to-one correspondence. This set is not countable, therefore it must be uncountable. All right, so that is actually most of the material that we're going to talk about today, and I think now's a good time to just consolidate what we've learned and sort of summarize everything. So at this point, we can basically say a set like this is finite. Again, finite sets are considered countable. And then what we've seen here today is that all three of these sets are countable, countably infinite. So the naturals, the integers, and the rationals are countably infinite. And believe it or not, this will play a very important role in your advanced classes later on. In particular, the statement that the rational numbers are countable, there is a lot you can do with this. The only set we have seen so far that is not countable is the real numbers. And again, the reason this is uncountable is because on the previous slide we showed that the interval bracket 0, 1 is uncountable, but that's contained inside of the reals, and so the reals are also uncountably infinite. Another thing we might want to do is just sort of arrange these into an ordering. So on the one hand, we have finite sets like these. Finite sets have cardinality that is strictly less than the naturals. So if you're finite, your cardinality is strictly less than something that's infinite. All three of these sets have the same cardinality. These are all countably infinite. And then these sets are strictly less than the reals in cardinality. Is there anything else we can do, though? Well, it turns out you can prove this, that if you have a set and you take its power set, you get a set with larger cardinality. So this set, the power set of the reals, which we could talk about, this is the set of all subsets of the reals. This set has cardinality which is larger than the reals. But there's nothing stopping us from taking a power set again. So the power set of the reals has a cardinality larger than this, and we can just continue in this way, and we can get infinitely many cardinalities. So not only do we have different levels of infinity, we have infinitely many different levels of infinity. And for that matter, we could take all of these sets and compute their union, and that will give us a set that has even higher cardinality than all of these. Then we could take the power set of that and get a set with even higher cardinality. So the world of set theory is this incredibly vast space with all this incredibly interesting structure. If you want to explore more about this topic, I would encourage you to look up information about infinite ordinal numbers and infinite cardinal numbers, which that explores this structure in a much more precise way. Now you might say, oh, okay, well this all seems kind of interesting, but isn't this just a bunch of sort of like abstract nonsense? Does this actually have any relevance to applied mathematicians? And as you guys all know, my background is in statistics, and I'll just mention one example where this concept of the different sizes of infinity has a real practical significance in statistics. So as a quick reminder, some of you guys may have had the calculus-based prob and stat class, and if so, you'll recognize the Poisson distribution. If not, that's okay. We can sort of go through this in a high-level way. But one example where this comes up is if you're looking at the number of alpha particles emitted by a radioactive sample. This type of random process has the following probability distribution, and the name for this is the Poisson distribution. And, if you're counting the number of alpha particles emitted, you're going to get 0 or 1 or 2 or 3. You're not going to get a decimal number. It's a discrete event. It's almost like counting the number of people in a city. That's going to be a whole number. It's going to be a natural number. It's it might be 2000 or 2001 or 2002, but you're not going to get decimal numbers in that process. So for this probability distribution, this is the distribution you use. And whenever you want to calculate a probability, you simply add up the probabilities. Like if you want to find the probability that x is between a and b, you're simply going to add up all of these probabilities from a to b in this way. And for those of you who had the prob and stat class, this was covered in chapter 2, and this is called a discrete probability distribution. But then there's another type of probability distribution called a continuous probability distribution, which was covered in chapter 3 of that course. And an example of this might be if we let x be a measurement error. A measurement error can be a positive or a negative number, and it can be a decimal value, right? Like if you're measuring something that's 10 centimeters long, you might be off by 1 centimeter, but you could also be off by half a centimeter or 0.7 centimeters or 0.2348 centimeters. So these measurement errors can potentially be any positive number, any negative number, and that does include fractions and decimals. And a common model for this type of phenomenon is the normal distribution, which has this probability density function. Now, if I want to find the probability between A and B up here, we simply add it up. We performed a summation of these values. But if we want to compute a probability in this context, we do an integral. So we would say the probability that x is between A and B is the integral from A to B of f of x dx. What does that have to do with the Foundations of Mathematics course? Well, we all recognize what this set is. This is the set of natural numbers. So, we could actually express it in this way. This is not a common way to express things in a statistics book, but technically this is what's going on here. Whereas what is this set? This is the set of all real numbers. So the fact that this is countably infinite is precisely why you handle this with summations, and the fact that this is uncountably infinite is precisely why you have to handle this with integrals. In fact, the definition of a discrete random variable in this course is that the support is countably infinite. If you go back and look at the notes, that is actually what it says. And then we sort of walk around that concept just in case there's any students in the class that haven't seen that notion from a theoretical math course, but that is really what's going on. And then there's all this material. If you go back and review the material from that part of the course, you'll see there are all these differences between discrete random variables and continuous random variables that can be explained by the fact that this is a countably infinite set and this is an uncountably infinite set. I'll just give you one more quick example. If you're talking about a discrete random variable, the probability of a single point could be 0, but it could also be a positive number. If you're talking about a continuous random variable, the probability of a single point is always 0. And yet, somehow, all of those probabilities can combine together to give you the probability in some range, which is not 0. And that might seem kind of counterintuitive, but if you go back and review the definition of a probability distribution and you kind of look at some of the details, you'll notice that an important part of probability distributions is they're intimately related to the idea of countable infinity. So when you have countable infinity, you can add things up like this and everything works out. You can even do infinite sums as long as they're countably infinite sums. But as soon as you get into this uncountable territory, all that goes out the window, and then you're forced to deal with integrals in this way. All right, guys. Well, anyway, that's it for this topic, and these are the homework problems. And as always, just let me know if you have any questions, and I hope you have a great day.